All right. So today we're very, very happy and excited to have Kai-Hao Yang presenting privacy preserving signals. The seminar is going to go for 1 hour. There's 45 minutes of the presentation, then 5 minutes is going to be given to Nima Haghpanah for discussion, and then 10 minutes at the end we'll reserve for questions. Now, if during the presentation, if there's a clarifying question or a short question, feel free to raise a hand or post it on the chat. But if you have a question that is kind of fairly long, please leave it until the end. All right. Without further ado, Kai, floor is yours.
Okay, thank you very much. Can everyone hear me? Yep. Okay. Yes, thank you for the invitation, and I'm excited to present a paper with Philip called Privacy Preserving Signals. And just on a very high level first, we're here in this project thinking about disclosing or how to model, how to think about information without telling people something that they're not supposed to learn about, and hence privacy preserving, right? And I'll be very precise in a moment what I mean by that. So without further ado, let me jump right into the model, if you agree. Okay, so here's the model. Let's fix a probability space. Right? And without any further structures, just except for standard Borel. I have a probability space that's standard Borel consisting of omega and a unit interval. This omega here is the relevant state of the world. Everything that's economically relevant is summarized by this omega. R in this unit interval is just a randomization device so that I can randomize my signal realizations conditioned on state even. There's some sigma algebra on there, and P is the probability distribution over this probability space. We can think of this as a prior, right? In this world, P is the product measure that's measure over omega cross the Lebesgue measure. Think of this as the prior. A signal can be modeled as a random variable that maps from omega cross 0, 1 to some measurable space S. Right? This is completely equivalent to Blackwell experiment, the distributional approach of modeling signals, in the sense that take any Blackwell experiment, I can find a signal that represents it, and take any signal that corresponds to a Blackwell experiment. Right, so this is just for convenience, and you'll see in a moment why we choose this modeling approach. All right. So far, everything is standard, right? There's some underlying state of the world, some randomization device, some prior, and you have a signal that depends on the state of the world plus some other noises. After observing the signal realization, you can update your belief and learn something about omega. So far, this is standard. And now we want to introduce a notion of privacy in this rather canonical framework. And to do so, let's start with a collection of events, which we call privacy sets, denoted by calligraphic P. The calligraphic P, the privacy sets, are subcollections of the underlying sigma algebra of omega. And the universe of possible events contains some events that are privacy sets. Those are things that we want to protect. And we're going to require these privacy sets to be closed under finite intersections, in the sense that if you want to keep two things private, you better want to keep the intersection of these two things private. For example, if you don't want to disclose whether an individual is male or female, and if you don't want to disclose whether this individual is young or old, then you better not want to disclose whether this individual is a young woman or an old man, right? Take any arbitrary collection of events that are closed under finite intersections, call these privacy sets. That's the primitive of the model. And now we want to introduce the notion of privacy. We're going to say that a signal S is privacy preserving if for every privacy event P, the posterior belief you have about this privacy event stays the same as the prior for all signal realizations you observe. Right? So this is saying that a signal S is privacy preserving if it doesn't allow for any Bayesian updating regarding the events that you want to protect. If there's some signal like this, we're going to say this is privacy preserving. Now, as an example, right, a signal that doesn't tell you anything, the degenerate signal is by definition privacy preserving because your posterior belief is always the prior. There might be others. And at this moment also, you might be thinking, is this condition too strong? Right? That by requiring my posterior to be exactly the same for all signal realizations and for all privacy events, is that a little bit too strong? And I would say I agree. And I'm going to tell you later on in the right moment how to relax this and how we can relax this. But let's stay here for a moment because this leads to a cleaner characterization. But the short answer is that we can generalize this. All right. Okay, so that's the model. This is the model for the entire talk. That's the model slide. Given this model, the question we want to ask is simply, what are privacy-preserving signals? What can we say about them? And in particular, what are the signals that are, quote, the most informative in Blackwell sense, that are also privacy-preserving? Okay? Okay. Now, let me use a rather stylized and simple example to illustrate some of the main points of our results and some of the motivations as well. Let's suppose that the state of the world is a product space of a unit interval and a binary characteristic. Suppose that this unit interval denotes a potential employee or a worker's productivity. And this productivity is under quotation mark because we're not going to specify payoffs just yet. Right? We can think of productivity as some proxy of output, but productivity doesn't necessarily translate into output because, for example, there might be historical reasons for discrimination that this quote measured productivity doesn't necessarily give you higher output or higher profit. The second component of the state in this example is a binary characteristic. Let's think of this as race. And suppose that in this world there are two types of people, blue and red. Right? This is the state space. The privacy sets here are like this, and that translates to I want to protect racial information. Whatever signal I give you about productivity, I shouldn't allow you to learn anything about race. Right? And now let me describe the prior. The prior can be described by this picture. The state is a unit interval cross a binary characteristics, which are two unit intervals. Suppose that these are the conditional densities of productivity given each characteristic. And just for clarity, let's suppose that the median of these two densities are here, respectively. And to complete the description, let's suppose that the marginal distribution over characteristic is uniform. So there's half of the population who are blue, half the population who are red. Right? So this is an example of the state space and prior. Now let's start thinking about signals. Here is a signal. I'll give you an example of a signal, right? Signal is a function that maps from the state of the world to some set of signal realizations. Here's an example. Right? I have a threshold, the dotted line, and the signal gives you a label plus if a person's productivity level is above this threshold. And likewise, it gives you a label minus if the person's productivity level is below this threshold. Right? This is a signal. Is this signal privacy preserving though? The answer is no, right? Because according to the definition, for a signal to be privacy preserving, my posterior belief better not change. My posterior belief about race better not change after seeing a signal realization. But here, if I see a signal realization plus, the likelihood ratio is different here, right? There's more blue people in the plus category than red people. So I'm going to update. I'm going to update and think that it's more likely for this person to be blue after I see the signal realization plus. And therefore, the signal is not privacy preserving. Note that, importantly, the signal that I just described, when I described this signal, I'm not referring to race at all. I didn't have the word race in the description of the signal. The signal only tells you plus and minus depending on whether this person's productivity level is above or below the threshold. This is because in terms of distribution of productivity and race, they are correlated. This is somewhat the central spirit of statistical discrimination. Race and productivity are correlated. So even if I only care about or try to give you information about productivity, sometimes inevitably I'm going to pick up some correlation with races as well, and hence not privacy preserving. So what are privacy preserving signals then, besides the trivial one that doesn't tell you anything? Right, here's another example. It's still thresholds, but now two thresholds, right? I have two thresholds at the median of each group. And I'm going to tell you plus if this person's productivity level is above the median of their own group. Given this signal, if I see plus, by definition, this is the median. So there are 50% of people here, 50% of people here. The likelihood ratio is the same. Your posterior belief is not changing. Likewise, after you see minus, your posterior belief is not changing. And therefore, this signal is privacy preserving. And it tells you something. It tells you something about productivity. It doesn't tell you whether a person's productivity level is above a common threshold, but it tells you whether this person's productivity level is above the median of their own group. So that still tells you something. Now, the label plus and minus here really are not important. Right? I could have flipped the order and tell you plus if a person is blue and has a productivity level above the median, or this person is red and has a productivity level below the median. That is still privacy preserving. It gives a different kind of information, but still privacy preserving. Now, there might be a question of why this signal is ever useful. I'm going to give you an example why such a signal is useful later, but this is a privacy preserving signal that tells you something different than the first one, right? So overall, in this world, one might then want to ask, so now we have seen one example of not privacy preserving signal and two examples of privacy preserving signals. One might want to ask, what are all privacy preserving signals here? And in particular, if my signal has to be privacy preserving, what's the most information about productivity I can give? Okay. Okay, now let me jump to a second example, which is going to be, I believe, the conclusion of this talk as well. I'm going to pose the question first, and then after I tell you the characterization and how to, and then in the last few minutes, I'm going to use this as an illustration of how and where our characterizations can be applied. So let's consider a rather general environment. Suppose that there is some underlying outcome, and I'm going to call this gamma. And suppose that I have a bunch of observable characteristics. I'm going to categorize them into three categories. One, materially relevant. So these are legitimate characteristics that are believed and established as legal to be used to give predictions about outcome gamma. There are protected characteristics called that theta. Those are the things that I want to protect. I can't use and I can't disclose. And a bunch of other characteristics. Right? Just to fix ideas, suppose that we might be looking at a bank who's making loan decisions, which could very well be very complicated, like whether I want to give loan, what the interest rates are, what the collaterals are, and what's the repayment schedule, etc. Gamma in this world is default probability, whether this person is going to default or not. Why is this person's credit score as established as some materially relevant characteristics about, for predicting whether this person is going to default? Protected characteristics, for example, race, and a bunch of other things, Z, say zip code, right? Now, a statistical model in general, or one could think of this as an AI algorithm, right, takes inputs the observables and generates an output S for a prediction of outcome gamma. Taking this model, a decision maker observes the output and then chooses an action A to maximize some expected payoff. That depends on output gamma, that depends on outcome gamma in action A. Right? Now, here the same thing pops out. Protected characteristics theta might be correlated with gamma. So if you're using, or in fact, if you're using efficient and very good statistical models to just predict the outcome gamma, sometimes you might pick up the correlation, right? And the prediction score S might be correlated with theta, and hence your action might be correlated with theta. And that's, some people call it statistical discrimination. The fact that theta is correlated with gamma means that it gives you some information. And it would appear to be that the action is taken in a biased way against some thetas. In practice, a way to regulate or discipline the degree of statistical discrimination in legal and computer science context, one of those is called no disparate impact. This notion says that, yes, there might be statistical discrimination, but nevertheless, I'm going to require the action taken, in this case by the bank, to be independent of theta. Or we can relax that to be conditionally independent, conditional on whatever is materially relevant. Right? Now, given that I have this constraint, that I don't want to be sued under the Civil Rights Act by creating disparate impact, what's the best kind of statistical model that I can use to make my loan decision? So this is a kind of applications that we can deal with after we see our characterization. All right. Okay. Now quickly about related literature. There are several streams of literature that this paper is related to, starting from Blackwell. The characterization we give is in the spirit of Blackwell. That's completely independent of the underlying decision problems. That later on, we're going to use the characterization to look at applications. But in terms of characterizations itself, it's independent of, it's decision problem free.
Can I jump in with a clarification question? Can you go,
Yes.
This is Larry White. Can you go back one slide?
Yes.
And the last line,
Yes.
no disparate impact. The action is independent of, does that mean not correlated with? Or what does independent of
Correct.
mean
Yes.
in this?
Not correlated with, yes.
Not correlated with.
Not
Okay.
correlated with,
Good.
right.
Okay, good. Thank you.
Thank you. Right. And there's, as the example suggests, there's the second stream of literature in statistical discrimination and algorithmic fairness that's developed in computer science for a while and recently in economic literatures. The third literature is about information and privacy. And there are several related papers here. And here I want to quickly highlight a paper by Hull, Sander, Mirsky, and Tammuz. If you are familiar with this paper is studying a, this paper starts from a different question. They're asking, given that there is an underlying state of the world and multiple agents, how do I give information about the state of the world to multiple agents subject to a constraint that none of the agent signals are correlated with others? So no agents can use their own signal to predict other agents' belief. Now, they characterize the sort of most informative, what they call private information structure. If, however, we specialize to a binary state environment, binary state and binary and two agents, and treat the second agent as a dummy player, that second agent's information can be thought of as something that we want to protect. So private signals in this special case, binary state, binary characteristics, becomes a privacy preserving signal. And therefore their characterizations can also be applied to understand privacy preserving signals in the binary state special case. And later on, I'm going to show where our results generalize that. All right? Okay, so now let's move on to characterizations. And check time. Okay, good. To begin with, let's just warm up a little bit. Let me give you the definition of Blackwell. But I'm assuming many of the audience is pretty familiar with that, so I'm going to go rather quickly. I'm going to say that a signal S tilde is Blackwell dominated by a signal S if, for any decision problem, a utility function and a set of actions, the decision maker is better off under S than under S tilde. So signal S Blackwell dominates signal S tilde if, regardless of what the underlying decision problem is, the decision maker is better off under S. In that sense, F gives more information than S tilde. And if I have two signals where one dominates the other and vice versa, in the Blackwell order, I'm going to say that these are Blackwell equivalent. Okay. All right. Now, the first step is the following. Remember, we started with a bunch of privacy events, a collection of events that we want to keep private. These are sets, and sets are sometimes hard to work with. So the first observation is that we can actually represent these privacy events by something that's easier to work with. And what are the things that are easier to work with? Well, let's go back to our first example. The underlying state space there is a product space. There's one component that's relevant, and there's the second component, which is raised there, that we want to protect. And that's more tractable because we can think of the second component as a variable rather than just sets. Turns out this is general in the following sense. Right? Fix the primitive privacy sets. This lemma says that there always exists a random variable such that for any signal S, the following are equivalent. S is privacy preserving in the sense that I just defined, and S is independent of theta. And this means that for whatever privacy events I'm given with, that I started with, I can always represent those events by a random variable theta and think of privacy preserving just as independence in the usual statistical and probability theory sense. So our question now becomes finding a signal S that is independent of this random variable theta, and then ask what's the most informative, what are the most informative ones in Blackwell sense. Okay. Now, before I give you the characterization, there's a little bit of work to do. So this is probably the most intense 2 to 3 slides for this talk. I'm going to define something first. I'm going to say that a signal is conditionally revealing if the signal S together with theta, the things that we want to protect, jointly reveals the state omega. If that's the case, I'm going to say that the signal S is conditionally revealing. Now, note that we're still in the thought experiment of Blackwell, right? We're gonna observe a signal S. This theta here is just something that we use to represent privacy sets that we're not going to observe, and in fact, we're not supposed to learn anything about. And so this definition only says that in a hypothetical world where theta is known, then putting together S and theta, I can fully back out omega. If I have such a signal, I'm going to say that the signal is conditional revealing. In particular, this definition itself doesn't suggest any kind of informativeness of conditionally revealing signals because you don't observe theta. Right? And yet, we have the following proposition. This proposition says a signal is privacy preserving if and only if it is Blackwell dominated by some conditionally revealing privacy preserving signal. Right? So let me unpack that a little bit. Right? We started with a question of what are privacy preserving signals. This is kind of an answer. A signal is privacy preserving if and only if it's garbling. It's Blackwell dominated by some signals that are like this, that jointly reveals omega together with theta, and at the same time privacy preserving. Right? And because of time, I can't give you the proof, but the proof is quite intuitive, especially one of the directions. A signal is privacy preserved whenever a signal is Blackwell dominated by some privacy preserving signal. That signal must also be privacy preserving. So the rest of the proof becomes fix any privacy preserving signal. Can we find a conditional and revealing privacy preserving signal that Blackwell dominates it, right? And because of time, I can't give you the proof, but the proof is still quite intuitive. But that gives me this proposition. Now, if I'm a bit more lazy than I am today, then we could just call it a day. That could be the end of the talk, because that's an answer. That's a characterization of privacy preserving signals. I am not. I'm rather a bit more energetic today. So I want to push a little bit harder. And in particular, this characterization characterizes privacy preserving signals by conditionally revealing privacy preserving signals. That kind of feels like cheating. I'm just defining a new thing and just push forward the characterization. That essentially is only throwing the question to what are conditionally revealing privacy preserving signals then? Right? Do they exist? Can we construct some of them? And how should we understand these signals? And that leads me to the following. Right? What are conditionally revealing signals? How to find them? So for the next 2 slides, I'm going to give a recipe of how to construct conditional revealing signals via a rather operationalizable procedure, right? To begin with, let's take any one-dimensional random variable defined on the state space omega. Any one-dimensional random variable, call this phi. And let me let f phi be the CDF of this random variable conditional on each realization theta hat of theta. If this f phi is continuous, then from the first lecture of graduated econometrics, we know that this random variable, q phi, defined as f of phi given theta, overall as a random variable, is uniformly distributed, conditional on each theta hat. Q being uniformly distributed, conditionally on each theta hat, means its distribution doesn't depend on theta hat, which then means Q is independent of theta, which means Q is privacy preserving. And here the formula is slightly more complicated because F may not be continuous. By defining Q this way, I can have the same property even if F might be discontinuous. Right? So now we have a particular signal, Q phi, called the quantile signal, that is privacy preserving. Furthermore, if we look at this Q phi, it turns out that if I had known theta, if I had known the realization of theta, which I don't, but if I had known the realization of theta, and if I see the realization of Q, I can back out the value of phi. Right? So in other words, Q phi conditionally reveals phi. Doesn't necessarily conditionally reveals omega, but it conditionally reveals phi. Now, finally, the underlying probability space omega is standard Borel, which means there exists a Borel isomorphism. In other words, there exists such a random variable phi that is invertible. And so if I pick that phi, the Q phi constructed, the quantile signal, is conditionally revealing, period. Right? So now we have a signal that's both privacy preserving and conditionally revealing. The quantile signal Q phi is one such example. The remaining question becomes, what are there other conditionally revealing signals? And if so, how to find them? And The answer is I can find all of other conditionally revealing signals by just looking at and playing with this Q. And here's how. Okay? So let's step back a little bit and think about what's going on here. Remember, I started with an arbitrary one-dimensional random variable. And eventually, for it to be conditionally revealing, I picked one that's invertible. But this ordering on the codomain of this one-dimensional random variable doesn't matter. And we're not talking about decision problems yet. We're not talking about payoffs yet. The order on R doesn't matter. So intuitively, one would think that if I change the order while preserving the structure of this quantile signal, I should be able to also keep it privacy preserving and give some other different kinds of information that are useful. That's what I'm going to do here. I'm going to formally define a way to change the order of this quantile, which is implied by the phi I picked. All right. I'm going to say that a measurable function M is measure preserving if, when evaluated at a uniform random variable, it gives a uniform random variable. For any one-dimensional random variable phi, I'm going to call S a reordered quantile signal if for every realized theta, there exists a measure preserving transformation such that M of theta is Blackwell equivalent to Q. All right, let me unpack that. Let me give you a few examples to help understanding that. Here I'm drawing a diagram. On the horizontal axis, this is S. This is the realization of this reordered quantile signal S. On the vertical axis, this is the realization of Q, the realization of the quantile signal. The blue line is a 45-degree line, right? So if for every for every realization of Q, say Q hat, I tell you exactly Q hat, and I do this for all theta, this is the quantile signal. I'm seeing the realization of the quantile signal. If instead I look at this red line, which is Q equals 1 minus S, and tell you for each realization of Q hat, instead of Q hat, 1 minus Q hat. Right? If I do this, if I tell you 1 minus Q hat, then first of all, because Q is uniformly distributed, 1 minus Q is still uniformly distributed. And this resulting signal would still be privacy preserving. And two, if I see a realization of S, and if I had known theta, I can back out Q. And because if I see Q and if I had known the realization of theta, I can back out omega, this signal would still be conditionally revealing. Right? And that also suggests I didn't have to do this for all theta. I can mix and match. For some realized theta, I can disclose Q using a blue line. For some other realized thetas, I can disclose the Q using the red line. And in fact, I can also do this, right? I have a function where Q equals 2 times S modulus a half, where for each realization of Q, say Q hat, I flip a coin. If the coin comes up with head, I'm going to tell you half of Q hat. And if the coin comes up with tail, I'm going to tell you half of 1 minus Q hat. This is still uniformly distributed if my coin is fair, and it still conditionally reveals Q and hence conditionally reveals omega. Right? So all I'm doing here is are examples of these measure preserving transformations. So in that sense, I'm just reordering the meaning of the quantile space, potentially theta by theta. By doing so, I can generate a bunch of other conditionally revealing privacy preserving signals. And that leads me to the main characterization. This says, take any conditionally revealing quantile signal, Q star. A signal is privacy preserving if and only if it is Blackwell dominated by some reordering of Q star. Part 2, every reordering of Q star is Blackwell undominated among privacy preserving signals. So let me unpack that real quick. Part one of the theorem actually says the following, right? We started with the question of what are privacy-preserving signals. The examples suggest there might be a lot, and they might be complicated. Turns out, according to this theorem, all privacy-preserving signals can be generated by just one signal, Q star, via reordering and garbling. So if you just find a conditional revealing quantile signal, and in a moment I'm going to tell you how, find such a signal, reordering it and garbling it, you can get some privacy-preserving signals, and in fact, you can get all privacy-preserving signals. Part two, reorderings of this Q star, this quantile signal Q star, form the Blackwell frontier in some sense. These are undominated signals among all privacy-preserving signals. So if you have a privacy-preserving signal, then there must be some decision problems where the decision maker is better off under a reordering of Q star than under that privacy-preserving signal. Okay? So that's the first characterization. Now let me give you a few examples to make it more accessible. Let's suppose my state space omega is a product space where X is one-dimensional and theta is something I want to protect. My privacy set is generated by theta. In that case, I can just take Q star as the quantile of X conditional on theta. Right? So if, for example, in the first example I saw, I can just compute the quantile of productivity across different groups. And I'm going to tell you that number. I'm not going to tell you which group this person comes from, but I'm going to tell you the quantile of this person in their own group. That's a Q star. That's a valid Q star. And the rest would be just reordering it and garbling it. That would give you all privacy-preserving signals. Now, second example illustrates why sometimes reordering is actually useful. Let's look at an even simpler example where where X is binary and theta is binary. And these are the prime. And the rest is the same. We know that Q star is the quantile, and that's a conditional revealing privacy-preserving signal, which can in fact be represented by this picture. Because the quantile signal is conditional revealing, so we can think of it as which state X it reveals given its signal realization and given theta. So to read this picture, this means when theta equals 0 and when my signal realization is below a quarter, I can back out that X equals 0. Likewise, when theta equals 1 and when my signal realization Q is below 3/4, I can back out that X equals 0. Right? Here is another signal that's a reordering of the quantile signal using these reorders. In this signal, if my signal realization is below a quarter, and if theta equals 0, I know X equals 0. If theta equals 1 and my signal realization is below a quarter, I know X equals 1. Okay? Now, if we look at the second signal, that looks kind of funny because in terms of information that's disclosed about theta, by definition, it's privacy preserving. So you shouldn't be learning anything about theta. In terms of information disclosed about X, if I have a signal realization that's below a quarter, X could be 0 and 1, depending on theta, but I don't know what theta is, so I don't know anything about X. I don't know anything about X either when my signal realization is above a quarter. So this signal is actually saying the following. It says that it doesn't tell you any information about theta or X, and yet it's a reordered quantile signal. So according to the theorem, it's actually undominated. And the question is, why is it undominated if that doesn't tell you anything? That's kind of funny. The answer is, this signal actually tells you something. The signal tells you perfectly the correlation between X and theta. It tells you exactly whether x equals theta or not. So if you have a decision problem, who doesn't care about marginal x or marginal theta, but cares about whether x equals theta, then for that decision maker, this reorder quantile signal must be optimal, because that gives everything you need. All right. Now let me quickly wrap up by telling you a few more things. One potential complaint one might have about the main theorem is that there is still a lot of reordered quantile signals flying around. There is an entire Blackwell frontier. So to answer what signal is the most informative, one could say that there is still a lot of answers, there are a lot of multiplicity, and some people might not like that. A potential way to sharpen this is to give up the full-blown spirit of Blackwell, and just, if we're willing to make some assumptions about the underlying decision problems, then maybe we can say more. So now suppose that I'm interested in only problems where the distribution of posterior means or posterior expected values that matter. For example, if I have a decision maker whose payoff is linear in omega, or in some statistic phi, in that case, can we say something more about privacy preserving signals? So let's take any statistic phi and let f phi be the CDF of phi. This is a known fact, right? And in fact, in the past 20 years, probably a lot of papers are written based on this fact. A CDF is a distribution of posterior means for some signal S, if and only if that CDF is a mean preserving contraction of the prior distribution. Now, this is a known fact. Can we have a similar kind of characterization for privacy preserving signals? And the answer is yes. The answer depends on this F bar, which is defined mathematically as follows. But really, F bar is just a distribution of posterior means induced by the phi quantile signal, which we just constructed. Right? With this, we have the following theorem. For any random variable phi, a CDFG is the distribution of posterior means induced by some privacy-preserving signal, if and only if G is a mean-preserving contraction of F bar. So to understand this better, the known result has this MPS structure without privacy constraint. This characterization says every restrictions imposed by the privacy concerns, however complicated the privacy sets are all summarized by this MPS upper bound. And in the meantime, the entire MPS structure of feasible distribution of posterior means is preserved. So a consequence of this would be, take your favorite paper, take your favorite economic problem that applied this fact and derived characterizations using this fact. We can kind of add privacy concerns into those results for free, because the entire MPS structure is preserved. The only thing that changes is the MPS upper bound. Okay, now my time is almost up and running out, so let me, as promised, conclude with the application. Right? Remember, we had this application about statistical discrimination, and we now want to ask the question of how to find the best algorithm or statistical model that does not violate no disparate impact and gives the most information. Using our characterizations, let me skip this, we have the following result. So let's suppose we're looking at binary state environments. In that case, a score S is just one dimensional, because that tells you the probability, the predicted probability of gamma equals 1. Then the following procedure gives you an optimal no disparate impact statistical model. Step number 1, identify the materially relevant characteristics. This might not be an economist's problem. This is probably the court's problem, or politician's problem, or lawmaker's problem. What characteristics should be identified as legit? Once we have that, just throw whatever algorithm you have and throw all the covariates you have into the statistical model and generate a raw prediction score, S, which is a number between 0 and 1. Step number 3, require a post-processing step so that one computes the quantile of the predicted score S conditional on protected characteristics and materially relevant characteristics. Then you're going to get for each individual a number, an orthogonalized score that tells you something about this person's relevant outcome, gamma. Then you make decisions based on that. This gives you a procedure that's completely separable, right? It has 4 steps. Step 1 is lawmaker's problem. Step 2 is an econometrician or a statistician's problem. Step 3 is the regulator's problem, and step 4 is the decision maker's problem. Here, you can kind of decentralize it. Every person can do whatever they're the best at doing this without worrying about statistical discrimination, and yet the result is going to give you the best statistical model that does not violate disparate impact, and it's the most efficient one among all, and it works for all decision problems. This is completely detail-free. Okay, so let me quickly conclude by, there are a few other applications we talk about in the paper, which I didn't have time to go through. And there are some other further applications right here ranked by the degree of confidence we have that this could actually work. And without further ado, let me just conclude here. Thank you.
Thank you. If you can switch off the slides. Nima, it's you've got 5 minutes. Please, floor is yours.
All right, you guys see my slides? Okay, thanks Kai-Ha for the beautiful talk. Thanks to organizers for giving me the chance to discuss this paper. It is full of really nice ideas and really nice results, so I encourage everybody to read it. I like to think about price discrimination, so I'm going to mostly talk about a price discrimination application of the results that the paper studies in one of the 4 applications. So suppose you have a joint distribution over consumers' values and their characteristics. So this, as Kai-Ha said, could be, is this person male or female? And this is how much they're willing to pay for a product. Suppose that the conditional distributions of values for each of the 2 characteristics is as drawn in this picture. Now, suppose we want to give the seller some information that the seller can use for price discrimination, but we don't want this information to reveal anything about what we want to protect here, these thetas. The paper says how we can do this. One way we can do this is to say, well, we're going to draw one type at random. The characteristic is either going to be theta 1 or theta 2. Suppose it is theta 1. Then all we can do is to tell the seller what the quantile of the value is according to the right conditional distribution. If we do this for each theta, when we think about the distribution of quantiles, this is just going to be a uniform number from 0 to 1, which means that no matter what theta we have the same distribution of quantiles. So by learning the quantile, the seller learns nothing about theta. Now, the paper gives a condition under which giving the seller this quantile is in fact the profit maximizing, privacy preserving signal. That is, this is the best information we can give the seller that maximizes the seller's profit subject to being privacy preserving. And that condition, as I understand, is that assume that these 2 distributions are kind of close to each other, so that when the seller learns the quantile, now the seller thinks, well, with some probability I have this value, with some probability I have that value. the seller ends up choosing the low price, so to sell to both. And the paper says under this condition, this is in fact the optimal privacy-preserving signal for the seller. So I thought for a while, can I prove this result without using the abstract results of the paper by perhaps using the structure that this problem has, which has a lot of structure? I couldn't prove it. So this tells me that, you know, there's something very fundamental that this paper is doing without using the properties of specific applications, but pointing out at what is important to us so that we can use it in so many different applications. Something else that Kai-Hao pointed at is that when we are giving this information to the seller, we tell the seller what the quantile is. The seller is going to end up charging a price that is independent of thetas. Why? Because the quantile is independent of theta. And if the seller is choosing a price based on a quantile, the prices end up being independent of thetas, which is a nice fairness property in the sense that the seller is not offering different prices to different groups of consumers. And I thought that for a while, this connection between privacy preserving and fairness, I think is a very interesting connection. And I didn't fully appreciate it until I had to think about it for a while and check some things with Kai-Hao and Philip, which is what we have learned so far is that if we give a decision maker a privacy preserving signal, then that decision maker's optimal decisions are naturally fair in the sense that they're independent of the protected characteristic. But what if we just start from the fair problem? That is, suppose you have a decision maker that already has all the information in the world, can completely observe the values and the states and the characteristics. But we require this decision maker to make fair decision. We say, whatever you do, your actions must be independent of these characteristics that you want to protect. Now it's not about protection of characteristics anymore, it's about fairness. Your decisions must be independent of thetas. Is it necessarily the case that when this decision maker ends up making optimal decisions, their decisions are as if this decision maker is choosing a privacy preserving signal and making an optimal decision for that? This other direction was not so obvious to me, and Kai-Hao and Philip confirmed that it is in fact true, that the optimal fair decision, we can think about it as coming from some privacy preserving signal and making optimal decisions for that. So I think this is a super interesting connection that this paper is discovering between privacy and fairness that is not obvious a priori without having seen what the paper is doing. Kai-Hao mentioned some relaxing this definition that currently the privacy preserving is binary. It's either privacy preserving or not. I think it would be nice to think about approximate notions. I think Kai-Hao suggested that they have some such definitions in the paper. I think this would be super useful to think about trade-offs. Now, how much privacy can be sacrificed, you know, and how that affects efficiency or other measures that we have. I think this would be very useful to have. I think I'm absolutely sure that there's going to be a lot of follow-up work. This is a really useful definition, and the paper shows already so much promise about it. Just thinking about the price discrimination application, for me, I think there's so many exciting questions to ask, and I think this toolkit is going to be very useful for it. So thank you so much. Thanks, Kai-Hao, and thanks to organizers again.
Thank you.
Thank you, Nima. Thank you. All right, now we're in the phase for Q&A. So if anybody who has a question, please go ahead.
Sure. This is Larry White again. Can we come back to that credit choice decision? And you came back to it at the end, but you didn't tell, at least I didn't get, what does the decision maker do when he or she knows credit score, knows race, and knows zip code, and we don't want the information to reveal race? How is the zip code information going to get used?
Good question. So a statistical model or an AI algorithm is just going to take everything you have in there, right? So I guess one potential channel would be because race is correlated with outcome, but that's protected. So you don't want to pick up race information. But even if you ban this input and disallow or forbid people to use race, you could potentially approximate race pretty well by zip code.
Exactly. Yep.
Then you're gonna run into the same problem.
Yep.
So this notion of no disparate impact is really built or it's really trying to avoid that kind of problem, that kind of proxy issues.
So,
And therefore, the answer, the procedure that I just described at the end of the talk, is going to guarantee you that even if you use race or zip code or anything that's highly correlated with race, after orthogonalizing it, you're not going to pick up any of these correlations, and you're only going to pick up the things that's the residual information that's useful for predicting the default probability.
okay. Thank you.
Right, and this works for all decision problems. That means you could have multiple banks making all kinds of different decisions. Maybe some decides, maybe some has to pay more attention on setting the interest rate. Maybe some has to be more careful about setting the collaterals. Maybe some banks only have a simple problem of deciding to grant loan or not. For all these problems, this procedure is guaranteed to give you the best statistical model. Thank you for your question.
It sounds a little bit like the opposite of instrumental variables approach, no, where the race is an instrument, but instead of looking at the predicted values, you look at the residuals.
Yes. One could think of it that way, right? So I guess it's kind of like exactly. It's kind of like the opposite of instrumental variable. So one could think of the quantile signal as some kind of residual of the relevant state of the world being quote projected onto protected characteristics. So if everything is linear, suppose everything is normal, and you run OLS of omega on theta, then the residual is gonna be a privacy preserving signal, because if everything is normal, zero correlation implies independence. And so this is what we're doing here can be thought of as sort of a nonlinear general version of constructing and characterizing the quote residuals of projecting something relevant onto something to sort of isolate everything else.
Can I ask sort of question? Was very, very nice, very clear talk. And maybe I'm just confused, but at the moment, sort of what I think I understand is kind of if the decision maker takes the action,
Yes.
and that's what I care about, then I have this procedure how to do this.
Yes.
Now, in reality, I might care about this firm taking an action, and this firm now makes an offer that then someone can still accept or reject. So the zip code might sort of reveal to me, I don't know, whether you live in a snowy or not snowy part.
Yes.
Of the US, and now I can, if I'm evil and I want to still discriminate, can I use that you might respond to different offers differently depending on your type, your productivity?
I see.
To still discriminate
I see.
against the agent.
Right.
So that's, for example, this example that I learn, you know, whether X is very low or something like that.
Yeah.
But, you know, differently for different races, blue and red. It seems to me I could potentially try and now make an offer that is attractive to high productivity people, but not low productivity, and in effect discriminate.
Right, exactly.
Does that make sense, the question at all? Or?
Right. That's a very good question. So I guess if I may, a way to reframe your question would be, as Nima said, as Nima's observation suggests, if you have a decision problem, if there's a single decision maker, then after seeing a privacy-preserving signal, by definition, the action taken is going to be independent of protected characteristics. However, if you have a problem that's more than a single decision maker, if there's a principal and an agent, and the principal can further screen the agent based on different types of contracts, then after seeing a privacy-preserving signal, that doesn't necessarily preclude the principal's ability to further screen and extract information which is sensitive from the agents. That's the, is that essentially what you are asking?
Sorry, my internet just went out during the answer. So I'm not.
Yes,
but I think you said something. Do I mess up something like second-degree price discrimination in there? I use the contract to screen, and that's sort of where I'm going.
Exactly. And I think the answer is no. You're absolutely right. You won't necessarily be able to guarantee that the outcome of this screening problem is still privacy preserving, because then the principal is still able to the principal still has extra instrument to elicit these sensitive and private information. But thank you. That's a good question.
I will stop the recording and we can continue the discussion in more sort of informal way. So